Welcome to this lecture in the new series of lectures in group theory. In this lecture, we'll be looking at an alternate proof of the division with remainder theorem that we discussed in the last lecture. So this is a somewhat similar proof. You could say it's not very different, but it is definitely, I would say, different. And please don't ignore this proof, even though we have proven it in the previous lecture. Please don't ignore this proof because I find this more natural, and this kind of approach to this proof also leads to other consequences. In the future, we'll see applications. All right, so let me start with a simple problem, which we will use in this lecture. So fix any non-empty subset of natural numbers, or in fact, just any non-empty set. Sorry, I misspoke. So just S be any non-empty set, nothing to do with natural numbers, and F be a function mapping into natural numbers. The domain is S. So then the claim is that, then the problem asks you to prove that there is some element in S such that the image of little s under F is the smallest possible. So there could be multiple such S's, that's okay, but there is at least one such thing. And this is very easy. You just apply the well ordering principle to the image of F. Just apply the well ordering principle to this set. This is a subset of natural numbers, so it has the smallest element, and that's it. That's how you prove that. So I just want you to realize this simple fact. All right, so what does the division with remainder theorem say? It says that if b and d are positive integers, then there exist unique integers q and r such that b can be written in this fashion, divided into quotient plus remainder, and the remainder has a bound. So it's non-negative and it's strictly less than the divisor. And as we said, this is a very intuitive fact. We know this since childhood, but perhaps we never really proved it. Okay, in this lecture, we will not look at uniqueness, because uniqueness, as we saw, was a very simple consequence of just existence, or rather I should say it was very easy to prove directly. So we will look at an alternate proof of existence. That is what we will do. All right, so let's get started. So before we start the proof, we need a definition. So we will say that an element in n cross n, meaning fix b and d as natural numbers, we'll say that this ordered pair is good if there exist integers q and r such that b can be written in this fashion, divided into quotient plus remainder, and where r is satisfying this inequalities. So basically, b and d, a good pair is just those pairs of natural numbers for which this theorem holds. So those are good pairs, and what we really want to do is, our goal is to show that every b comma d in n cross n is good. Alright, so this is what we want to do. So collect the not good ones. So let S be those. Let me get rid of the grid, because that's how I want to do these lectures. So let S be those pairs of natural numbers such that this is not good. So as I said, bad means not good. Okay, so now the goal becomes to show that S is an empty set. So far we haven't done anything, but we just reformulated the problem into showing that S is an empty set. So if you realize it, then now we proceed. So assume on the contrary that S is not empty. Recall, this is the notation for the empty set. So assume S is non-empty, and now define f from S to, well, it is mapping into natural numbers as f of x comma y equals x plus y. So this may seem like coming out of the blue, but just think of f as a size measuring function. So you pick an element in S, and this you could think of as the size of the ordered pair that you start with. Right. So this is just a size of thing, size of the element that you pick. So since S is, we have assumed that S is non-empty, and by the problem that I stated at the beginning of the lecture, there is some S. So choose some. Choose B comma D in S such that f of B comma D is less than equal to f of x comma y for all things in S. So if you think of S as the size of something, what we have done is just pick the smallest bad thing is what we have done. Just pick the smallest bad thing. Okay. So there are two cases. So case one. Case one is that, let me use a different color. I like using different colors for cases. Case one is that B is less than equal to, or B is strictly less than D. So in this case, note that B equals D into 0 plus B. Trivially, of course. Where, since B is less than D and B is a natural number, where 0 is less than equal to B is less than D is satisfied. Right? So if B were less than D, B is already a natural number, so in fact this is a strict inequality, so there's nothing wrong with writing this. And B can be written in the fashion divided into quotient plus remainder, and remainder satisfies this bound. So what this means is that thus B comma D is actually a good pair. Is good, contradicting the choice of B comma D. B comma D is the smallest bad thing. Something is wrong with the software. Right, so this case 1 leads to a contradiction. Case 2, B is at least as much as D. Okay, so then consider the pair. Consider, in fact, this time what you can do is, so in this case, in fact, we could have clubbed this case with the previous one. In this case, B equals, okay, so let me partition this into two parts so that there is no confusion. So B is equal to D. Strictly less than D, equal to D, and greater than D. We'll do three cases. So if B equals to D, then B is equal to D into 1 plus 0. Where again, 0 is less than equal to 0 is less than D because D is a natural number. Right, so if B equals D, then this is trivially satisfied. And this is also, of course, trivially true. So in this case, therefore again, thus B comma D is good, and again this leads to contradiction that B comma D is bad. So lastly, we have the final case to take care of. This is more interesting than the previous cases. Case 3 is B is strictly greater than D. So now consider the pair b minus d comma d. And since b is strictly greater than d, this is a natural number and this is also a natural number. Now, f of this pair equals b minus d plus d, which is equal to b, which is strictly less than b plus d, which is equal to f of b comma d. So the size of this pair is smaller than the size of this pair, and since this was the smallest bad pair, this cannot be a bad pair, right? Because this was already the smallest bad pair whose size dominates the size of this one. So this cannot be a bad pair, therefore this is good. So thus b minus d comma d is good. And therefore, by definition of good, there are integers q and r such that b minus d is dq plus r and r is in this range. But this implies that b equals d into q plus 1 plus r and r is in this range. But this implies that b comma d is good. Which again contradicts the choice of contradicting the choice of b comma d, because this was a bad pair. So in all three cases we get a contradiction, and this implies that our assumption that S is non-empty, our assumption that S is non-empty must be false, and therefore S is empty and we have achieved our goal. So that's it, that's a proof. It's a slightly different proof than the previous one, and I find this more natural. You just measure the size of things which you don't like and pick the one with smallest size and you're done. And this is not the only measure of size that works. You can cook up other measures of sizes, no problem. This is the most easiest one. Just add the two things. Right, so I hope you followed this and enjoyed this reasoning. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.